So welcome everyone. It's a pleasure to have Sujoy Bhore from IIT Bombay among us. Sujoy is a faculty member in the CS department at IIT Bombay. He also has visiting position at the London School of Economics. His research interests are in the area of combinatorial optimizations, algorithms, and data structures, computational geometry. So Sujoy did his PhD from the Ben Gurion University of the Negev in Israel and had postdoctoral positions at TU Vienna and University Libre de Brussels. So over to you, Shija. Thanks.
Yeah. Thanks to Ashish for the introduction. Hello, everyone, and welcome to my talk. And first of all, I would like to take this opportunity to thank the organizers for inviting me to present at the STCS seminar. And so, am I audible at the back? Thanks. Yeah, so one theme of research that I have been doing in the last couple of years is largely under this umbrella of geometry and optimization. And you might have heard about this recent Ghibli image trend. So I asked ChatGPT that, can you give me an image where Pythagoras and Euclid is fighting over this topic in ancient Greek? So after several rounds of back and forth, it generated this, which I'm actually quite happy with this. But I should also tell that it doesn't take anything away from the hard work that Miyazaki did for years. So let me begin by my talk by just saying that objects play a very important and pivotal role in existence. They are in different forms and shapes like orthogonal, non-orthogonal, balls, spheres, convex, non-convex shapes, or different kinds of curves. And as Kepler said that wherever there is matter, there is geometry. So the modern story of optimization, basically like every complex digital process runs in today's world, starting from stock market to drug design to self-driving cars to chip design, to name a few, there is always an underlying optimization process which is playing an important role. And geometry has an important role to play in that regard. It has many applications, to name a few, in areas like robotics, in sensor networks, or routing, visualization, data mining, so on and so forth. So this is all like the application pitch, but if you are not convinced by those application things, maybe you are convinced by art. So this is a picture I took in Van Gogh Museum in Amsterdam. So Van Gogh apparently was very interested in objects like potatoes, for example. So because he liked like different kinds of shapes. Also, I mean, the artists go one step forward, like colors and lights and so on. And I found this quote next to this picture that he said, "I know they're difficult to sell, but it's devilishly useful."
What is there? The potato or the painting?
So, you know, the track record of Van Gogh during his lifetime, no painting almost was sold. So,
Yeah. What is that green line there? Is it part
this is a reflection.
Oh, I thought that was a cucumber. That's realism.
I think we'll leave it up to the interpretation. All right. So, primarily the two themes that I would like to talk today. One is independence, the other is packing. So independence set problem is like one of the most classical problems in theoretical computer science, has been studied since almost the inception of the field. In the geometric setting, we have a set of objects, and the objective is to choose a large subcollection of them, which are like pairwise disjoint. They don't overlap with each other. So that's like one theme of problems. So this is based on joint work with Timothy Chan, which appeared in Soda and Sosa this year.
The same book?
No. So yeah, I mean some simpler version, but like similar theme.
Independence.
Right. Yeah, independent work, but on independent sets. The other type of things that I want to talk today is on packing. So roughly speaking, imagine there is a hypercube in D dimension, and we want to pack a bunch of objects inside this hypercube. And this is actually based on joint work with Pritam Acharya, Aryan Gupta, Arindam Khan, Bratin Mandal, and Andreas Weisert, which appeared in iCalc 24. And I'm very happy to say that in this work, 3 of the authors were undergrad students from 3 different institutions. So I'm more happy about this.
Many institutions.
Sorry?
Packed many institutions.
Right, fact management. So I'm going to come to independent set, but with a little bit of a detour. I will first start with piercing set. And the reason is that because this style or this technique I'm going to use from here to the independent set. So imagine that you have a set of n geometric objects in a d-dimensional space. I mean, here in the example, we have a set of disks. And the objective is that I want to choose a smallest subset of points that hits or pierces all the objects. So, I mean, this is a problem of interest on its own. It has applications in wireless sensor networks or facility locations and so on. But in the theoretically speaking, this is a continuous version of the heating set problem. So, and then geometric heating set corresponds to the geometric set cover in the dual range space, and therefore it is also connected to the set cover. And we know since ages that if we take a greedy algorithm, this is already going to give us a log factor approximation. Of course, I mean, whenever I'm talking about objects, I'm assuming that they are of constant description complexity because, yeah.
What's the definition of piercing set?
Yeah, I want to choose a smallest subset of points that is going to hit all the objects.
So here the black dots.
Yeah.
We're not hitting all the objects.
Did I
Every object is one black dot.
Yeah. So in the geometric setting, you can say much more and you can get better algorithms. So due to Hotchpam and Mass since 1980s, we know that
The greedy algorithm requires using some intersection query set because so you use
Yeah,
set cover, but a set cover set.
yeah, because you
The
take it.
Cost is the implicit.
Yes, you take it to the dual, you do set cover, you kind of can.
But to go to the dual, you like so the sets are like they're essentially infinitely many sets.
Yeah, so
Constant.
I'm assuming in D dimension, but constant dimension. So probably I think that is your question,
No,
right?
but even the number of sets, like there's one set per point. Right? So
Yes, yes.
that's the rule. So there are uncountably many sets.
Yes, yes,
But there many of them are essentially the same.
yes, exactly.
So
Yeah.
it's like some kind of number of intersections, different intersections that you can get. That's the
Yes, yes.
But so that requires like being able to quickly search inside that.
Yeah, so you are under this intersection queries.
Yeah.
Right. So if you are in the geometric scenario, you can do much better. If they are, for example, near equal size fat objects, we know since 80s there is a 1 plus epsilon approximation. For arbitrary size fat objects, if we would just sort the objects and then choose greedily one by one, this is already going to give us constant factor approximation. So Timothy showed in 2003 that there is a separator based algorithm. This is similar in ethos of the planar separator, but an extension from there, because intersection graphs can also contain very large cliques. So you can get a 1 plus epsilon approximation. And then in SODA 24, Pankaj Agarwal, Sariel Hartelev, Rod Chaudhary, and Sintos. So they used this multiplicative weight and epsilon net to show that for arbitrary boxes in D dimension, you can get a log opt approximation running in n to the d by 2. Yes. Sorry?
What is a fact object?
Yeah, I'm going to define, but informally, like if you consider the largest ball inside the body and the smallest ball containing the body, that ratio is.
How's the input given?
Sorry?
How's the input layer?
So because we are in constant dimension, you can just explicitly give the input. Like you can just define, give the objects as it is, right? And also I assume constant description complexity. So
But the shape of objects are not controlled. It could be arbitrary.
yeah, it could be arbitrary, right? But because of the description complexity is bounded, so you can give with respect to like the hyperplane equations.
Arbitrary box is axis aligned? No, it's not axis.
No, this is axis aligned. That's a good point. Yeah, so this is axis aligned boxes. So the first question that I'm interested in is that the running time, as you can see, there is a dependence of the dimension. Can we actually get a near linear sublogarithmic approximation for the piercing set? And then also, can we bring it to the dynamic scenario? When the objects are undergoing insertion and deletions, can I maintain the similar approximation factor in sublinear update time? So it turns out, yes, that for boxes in D dimension, we get a near linear running time of n to the 1 plus delta with log opt approximation. This is actually a big improvement over the running time of Agarwal et al. Because they had n to the d by 2. For fat objects, assuming constant description complexity, we get a constant factor approximation in n to the 1 plus delta. And
what's the quantifier of delta here? It's true for every choice of delta.
it's true for every choice. I mean, you will see later that we're going to lose it in the approximation factor.
Okay.
Yeah. So I want to point out one thing. So typically when you talk about dynamic graph algorithms, so the natural model to consider there is edge insertion and deletion. And the reason is because you have the obvious degree barrier. So there can be one vertex that shows up and wants to be neighbor with everybody. And then in the next step, this guy disappears. So you can't do anything but to pay like linear over there. But we are in the geometric regime, and it is more natural to talk about actually object insertion and deletion than, I mean, you can talk about edge insertion deletion, which is like corresponds to object shrinking or expansion, but it's somewhat more natural of vertex insertion and deletion. And because, I mean, of course, one can think of these problems by taking into the intersection graphs and then applying the graph techniques, but you don't have to necessarily go to the intersection graphs. You could use geometric data structures to implicitly make these queries. So here we don't have necessarily the degree barrier. That's the point. And also another point is that when you take a static problem to the dynamic regime, you have some loss, extra loss that you suffer because you're trying to control the update time. So you have to pay for this in terms of the running time. But it turns out here it's like a almost lossless dynamization. So we can maintain like pretty much a similar factor asymptotically, like for boxes as well as fat objects. So let me give a glimpse of the technique that we are using, and then I will use this for independent set. Yes.
So these fat objects, are they convex?
No, not necessarily.
necessarily.
No.
So then when
They
you
don't-
describe them by like non-convex polyhedra? Like
Yes,
convex-
but I assumed constant description complexity. So they only have like some constant many sides. Otherwise, it is as you said, the description could be challenging.
But in other words, if you ask a question like piercing and so on, even a small error may not be permissible, no? Because you need to exactly get a point that is in all the sets.
Right. But I think if you have these two assumptions, right, that you have so I mean the number of times it can make a bend is like bounded by some constants. So then you can precisely define the object.
Was it like a union of convex?
Yeah, right. Union of convex sets also you can think of it that. Right. I mean everybody is a union of constant many.
Nice.
Okay, so I'm going to first describe a very special scenario and then I'll lift it up to the general.
Sorry, maybe
Yes.
maybe it's a failure. How careful are these algorithms about like I mean these are all like over real numbers, right?
So in computational geometry, there's always precision issue.
Yeah.
And in fact, if I eventually get to the packing part, then you will see also the sum of square roots business, right? Yeah. So there is always, you have to suffer a little bit loss. Yeah. So I'm going to first consider a very special case. Basically, in that case, I'm going to take in the input only some axis aligned boxes which are stacked by at least one of the hyperplanes among order B many axis aligned hyperplanes. Okay. And so this is basically give me or induce some kind of a non-uniform grid here. And so this set of axis aligned hyperplanes that I get a grid, I'm going to define equivalence classes out of this grid based on the following. So every object, they uniquely contain a subset of corner points or the intersection points of the grid. So So I'm going to put two objects in the same equivalence class if they contain the same subset of corner points. And then I'm going to pick a representative from each of these classes and kick out everybody else. Okay. So just because I have B to the D many grid cells, I have B to the 2D many classes, and because for every class I'm keeping only one, so I have the representative class size is B to the 2D. At this point, it's a very simple scenario. So at this point, we have multiple options to close this game, because if we are in dimension 2 or 3, we could use the epsilon net algorithm. Epsilon net is, one way to think is it's kind of a generalization of hitting set. So by Aronov, Ezra, and Sharif, if we are in dimension greater or equal to 4, then we could simply invoke the Agarwal et al. Because we have reduced the instance so much that it doesn't matter. So eventually, let's say that log, so we want to compute this log opt in B to the order 1 time. Now, this is not a piercing set. This is only a piercing set for the representative class. So I have to get the piercing set for the whole. So for every point, I'm going to take all 2 to the D many corner points, which is surrounding this particular point. And my claim is that this is going to be a valid piercing set for all. Why? Because imagine that in this scenario, from this particular equivalence class, this red object was chosen, and this red point is the piercing point for this object. So every other object, based on their definition, is going to interact with this particular cell. And if I'm taking all 2 to the D many corner points, which is defining this cell, at least one of them should be good enough to hit everyone else.
So what should I be thinking of B as? How is B in?
Yeah, I'll set up the B later.
Right. Okay.
What was stamped?
Sorry?
What is the box?
The intersects.
So then I don't know, isn't any object, every box starts with some hyperplane?
Yes, but I'm going to take only some bounded number of hyperplanes.
Oh, only from?
Yeah.
Oh, okay.
Yeah.
Every box to be stamped by one of these.
One of these hyperplanes.
By one hyperplane parallel to every
Yes.
axis.
Yes.
So just to make sure I understand correctly, you first want to identify a small set of hyperplanes such
Yes.
that instead of stabbing, if you had thought of it as cutting using the
Correct.
hyperplanes, then you cut every.
Right. Exactly.
Piercing, they getting stamped.
Yeah.
Yes.
So now from that, you want to somehow extract whatever piercing set.
Yes, exactly.
And to extract the piercing set, you basically for each cell that you produce using these B hyperplanes,
Yeah.
you chose one representative.
Yes.
And now for that you choose all.
Yeah, and then I choose the covering points around
Okay.
this grid, and then that is a full piercing set, at least for this instance.
Okay.
Okay, now I want to combine this lemma that I just described to the general version. And this is somewhat a B array version of the divide and conquer. So like, as Ramprasad earlier asked, like this, so the relation here is that in the approximation, you will have like 1 over delta to the D log of approximation in n to the 1 plus order delta time. And this one can also make this dynamic. Let me define a type J problem for every value of J between 0 to D, where I assume that given this S, this is tabbable by order B hyperplanes, which is orthogonal to the kth axis for every value of K from 1 to J. The previous problem that I just described, this was a type 0 problem, right? And now this type D problem can be solved by this lemma.
Okay, type 0 problem, you're replacing J by 0? I don't understand what.
I mean, this is just like, think of this as kind of, not replacing exactly by 0, but just saying that this is one type. And you have like all of these other types that I have to cover.
The previous one shouldn't it be a type D problem then? Because you want all of them to be stamped by each.
Yeah, so like that is the, yes, right. So the previous one that I described is type D, and the original problem is type 0. So I have to get it down, break it into hierarchical levels, and so here is the strategy that I'm going to follow. So for all J which is less than D, I will pick.
I'm a bit confused. Why is it looking like it gets better and better as D becomes larger? Because if I put delta to be like e to the power 1 by D.
Yeah.
then this is just order log of for every d. And
Yeah,
the-
but then you
but
will
the
have,
runtime is becoming better, like e to the power 1 by d. So that thing is going to n square as d goes to infinity.
but you want like near linear, right? So
No, but still,
want
like,
to-
it seems to be becoming better and better. Like it's becoming closer and closer to n square. As like it starts somewhere around n cubed or something, or n to the 4 or something, and then so that
What's your
so if you put delta to d to the power 1 by d, so the approximation ratio remains the same, but the runtime seems to getting better and better as d increases.
Hmm. I haven't. Yeah, maybe we can check this.
Okay.
Yeah.
So there is some other dependence on that.
Yeah. So
In the worst case is d equals 0, right? Then that would be okay.
But it seems to be weird. But like, if we just think of, I can take a problem in R to the 1 as a problem in R to the d. Right? Like there's no fatness content here.
I mean, there is a no. I mean, this is only for the boxes.
Yeah, so,
right.
so then
Yeah.
any problem in d equal
Yeah.
to 1 is also
But
probably-
the same should work also for the fat objects. Yes. Yeah. Yeah. I mean, okay. Let's
Yeah.
maybe.
So isn't the guarantee also getting worse? It will be a d to the d times log log.
No, delta is e to the power 1 by d. That's the delta is like e to the power 1
Oh,
by d.
I think delta is equal to okay.
Yeah. So to solve this type J question, we are going to build this B array tree. So for this, I'll pick B minus 1 hyperplanes, which is orthogonal to the jth axis, divide the space into like B many slabs, and each of them is containing roughly like n by B many corner points. So we're going to store the boxes in S that is tapped by B minus 1 dividing hyperplanes at the root. And then you recursively build this at every level, like build the subtrees for the subset of order n by B many boxes. Now we have like log Bn many levels of the tree, so we can compute the piercing set for each. So do it for each of these node and take the sum. Right? Does it make sense? So I'm not going too much detail of this analysis. This is not like very complicated as well. So for a type J problem, this satisfies the recurrence that f of j is less than equal to order log bn times fj plus 1 with fd equal to log log opt. So therefore, the overall approximation, you can bound it log bn to the t log log opt. And the running time, so because it is just happening like n times, and in the lemma we already showed that this is b to the order 1, so it's like n times b to the order 1. As you might notice at this point, the dynamic is very trivial because whenever we insert or delete an object, we can simply insert or delete it in one type J plus 1 problem. And then you update a type D problem by the lemma in b to the order 1. So, of course, there is one technical issue of like the tree balancing part, but this can be done by the standard weight balancing scheme. And then finally coming back to Ramprasth's question, so let's set b equal to n to the delta, and this is going to give us all the guarantees that we need.
Very simple.
Yeah.
Going back to how the input is specified. So given that you have objects.
Yeah.
How do you actually identify whether there is a point which is an intersection of?
I mean, these are boxes.
Yeah, even
So,
boxes. So what
you
kind
can-
of query are you making?
I mean, because it's in constant dimension, you can explicitly give the description of the boxes. I mean,
Essentially making the corner
Yeah.
present with the other box.
exactly. So I think that so I guess the doubt is like when you go in very high dimension, then this such kind of description. I guess if for boxes it's still fine.
You just take faces. They don't-
But for fat objects, for example, then it is a problem because you
Yeah.
cannot give this description explicitly. Then I think is more of what you does. Like you have to work in the query model. Like.
So here, so one question, so
Yeah.
going back to Piyush's thing. So here, should I be thinking of delta as something less than 1?
Yes.
Okay, so then e to the 1 over d doesn't work. Right?
Yeah, that's
Yeah, it's between 0 and 1. So
Yeah, okay.
delta is 1.
Yeah. Yeah, I mean that's why you get the near linear
Yeah.
also. So roughly this is 1 hour or
Yes.
one? So
We should
half an hour.
around 5 we will. Yeah. By 5 we will.
By 5. Okay. And so just one remark is that the previous algorithm was multiplicative weight update based method, and which uses like this distinction between the small opt and large opt. In our case, we don't need any of these things, and it's not really limited to LP or MW based methods. We also give another static algorithm using Monte Carlo randomization. But I should say that even though this has a slightly better running time, but it doesn't give the set per se, it is only going to give the value of the set. And the dynamic algorithms, of course, can be deamortized by the weight balancing trees and so on. So now I'm going to come to the independent set problem, which I promised earlier. So we have this set of n geometric objects. We would like to choose a maximum cardinality subset where like they don't intersect, like pairwise, there is no overlap. So if you notice that the size of the maximum independent set is always at most the size of the minimum piercing set. And already, I mean, the Hodgkin-Mass algorithm, this is also going to give a p-test for near equal size fat objects. For fat objects, there is a constant factor approximation. And then there are several p-tests that was developed in recent years. All uses many different kinds of techniques like shifted quad trees, geometric separators, local search, and so on. The case of rectangles, it's a very simple scenario, but surprisingly, it has been very interesting for independent set. And so we are given axis-aligned rectangles in the plane, like in 2 dimensions.
The rectangle is just a box.
Yeah, box in 2 dimensions. So
Axis parallel rectangle.
axis parallel rectangle. So the best, like, since 90s or even probably before, it's very simple divide and conquer algorithm gives you a log factor approximation. You can just take the median, find the best, and then keep doing this recursively. So the first major result on this was by Julia Sujoy and Parinia in around 2009. They showed that there is a log n approximation for this problem. And then Andy and others showed that there is a quasi-p-test using like separators and DP and so on. It was not known for a long time that whether there is a constant factor approximation for this question. So Joe Mitchell in Fox 21 showed that there is a constant factor, which Galvez et al. Subsequently improved it to 2 plus epsilon.
The Mitchell thing has no linear programming as well.
No, no.
It's just a recursion.
It's a recursive thing. I mean, it uses very similar technique of his TSP algorithm, which is like these guillotine separations and like constant description objects and so on. The problem is with Joe's algorithm and also the algorithm of Galvez et al. That they are polynomial time algorithm, but really high polynomial. So Mitchell's algorithm at least is n to the 23 years. So the question is that can you get in near linear, but like stay inside the constant factor regime? So yes, we can get a constant factor approximation for rectangles in the plane in n to the 1 plus delta time, and also for fat objects. So similarly, if you want to, now typically in the dynamic scenario, you also want to maintain this in sublinear update time. And by the way, like one point is that, I mean, inevitable recipe for going to static to dynamic, if you are expecting a sublinear update time, then you should have a near linear solution in the static case. Otherwise, I mean, you could just run the fastest dynamic every time and get a better static case. So we can maintain constant factor for dynamic rectangles. We can also our algorithm generalizes to the weighted case. So Mitchell's constant factor is actually for unweighted case. And for the weighted case, the best approximation still is log n. And we don't know anything better than this. But there is a quasi polynomial time approximation scheme. So I guess like there is a reason to believe that this is not the right answer. Yeah, so I'm going to follow the similar mechanism that I used for the piercing set. So I will just go over this fast. that I will again take the hyperplanes, define the equivalence classes, keep the representative. One point is that for the unweighted case, you can keep arbitrary representative. For the weighted case, you keep the best, like the one with the maximum weight. Now, for the unweighted case, one can use Mitchell's algorithm. For the weighted case, one can use Farinia and Bartos's result of log-log opt approximation. And now I'm going to claim that I made only constant factor blow up to the actual independent set. So there is a very interesting result in structural graph theory.
So you have to apply the Mitchell algorithm. How is the runtime? Because you
Oh, because I have reduced it to the this B to the
the
menu,
right.
right?
That is the
Right. Now, so the thing is that if you have a set of objects such that the depth of this object is bounded, then Parini and Bartos showed that this arrangement has, if the maximum depth is delta, then the intersection graph is delta log delta color.
Sorry, what does depth mean here?
So this is the largest clique you can think in that
Oh,
sense,
okay.
in the intersection graph. Or a point is covered by delta.
A single point is piercing like delta thing.
Right.
Okay.
So there is a very interesting problem for people interested in structural graph theory. So, I mean, we fairly understand the chromatic number landscape for various kinds of intersection families except rectangles. And here is the scenario. So for all fat objects and so on, the chromatic number is bound is tight, it's delta. If you go to strings, then I think Matushek's result from a long time back, it shows that, I mean, this becomes like horrible, these factors. I don't remember exactly right now, but it's bad. For rectangles, the best upper bound currently is delta log delta, but the lower bound is delta. So I don't know what is the right answer, the chromatic number. But anyway, since this is delta log delta colorable, so you could just simply use the coloring here. And now for, I mean, one can apply the similar type of argument, like if there is a point which was kind of hitting this one guy, you could take the corner points and this doesn't blow up. So one can simply take, for the unweighted case, the largest cardinality set from these colored classes. And for the weighted case, one can take the largest, like the color class that is giving me the maximum weight. And insertion and deletions can be simply handled by linked list per classes for the unweighted case and priority queues for the weighted case. We also have another probabilistic proof which does not use this coloring argument by Parinia and Bartos, but it doesn't give any explicit algorithm. It's just another observation. So yeah, so I think I'm going to skip over the approximation and running time details. And so I also this.
No, but so there seems to be a general thing here, like
Right.
solving. So there's a runtime improvement even though you're using a subroutine.
Yeah. So the point is that if there is any improvement over the, let's say, Mitchell's algorithm, so one gets a better running time over there. So with a little bit loss, you can bring into the near linear framework.
Wondering if there's more here, like is there something general here that like certain class of problems you can take over algorithms and convert them to near linear, but so there has to be some loss somewhere in this whole thing.
Yeah, so you are losing in the approximation, right?
Oh, approximation. Because it's not O1 anymore.
No.
Yeah.
No, it's O1, but you, if the respect to the
Trading of the approximation with the
running, right. But that's a very good question. Like that, what class of problems? We were more of like, I guess the theme was more what class of objects we can handle. But that's a good question. That what class of problems for which one can extend this framework. So I just want to kind of like quickly touch over this, that for the dynamic case, people take it one step further. They are not happy just with the near linear, the sublinear update time. They want polylog update time regime. And because, I mean, I think that the dynamic the independent set for objects was like first initiated by the visualization community because they have interest in labeling and this kind of stuff. So yeah, that's why this even at the expense of higher factor but polylog. So we know that there is a constant factor approximation from our work in sausage 24 that you can maintain a polylog approximation. Sorry, you can maintain a constant factor in polylog update time. And now we know that, I mean, there is a very simple algorithm. This is that SOSA word that that you can get like a polylog update time for like a large class of objects, for fat objects and so on, not for rectangles. So for hypercubes also we can do this, but we don't know how to do this for boxes. One point also, one can say that even though this is faster, this can only handle the unweighted case. But the previous framework that I defined, this also works in the weighted case. So, and everything that I mentioned here, they all also work for the piercing set problem as well. So actually this framework is a little more powerful, and it also works in other problems like vertex cover or matching. I mean, like just for the sake of completeness, in the vertex cover problem, given an undirected graph, you want to choose a subset of vertices such that every edge has at least one endpoint in the cover. So for vertex cover problem in intersection families, there are a lot of things known, and our question was that can we get a near linear time better than two-factor approximation for vertex cover? So it turns out that for rectangles, you can get like 1.5 approximation. For fat objects and so on, you can do much better. For dynamic case, this is the first time that we notice that you can do 1 plus epsilon approximation maintenance. It's kind of rare for geometric families for under vertex insertion and deletions. And for matching also, due to this recent breakthrough work by Sachdeva and others, that we know that bipartite graph, the matching can be solved in m to the 1 plus small of 1 time. But for intersection families, you can do much faster, like n to the 1.5 times log n, or n to the 4 by 3 plus epsilon. And I mean, so question is that can you maintain 1 plus epsilon approximation in polylog update time? And turns out that yes. So for disks, fat boxes, monochromatic, bichromatic, all kinds of cases. By the way, bichromatic one should just interpret as bipartite graph of bipartite.
Can we list the number of people?
Sorry?
How can the runtime be less than the number of people?
Because you don't have to explicitly define the intersection graph, right? So think of like you have two disks and they overlap. So you don't have to give that edge.
The
Right?
graph is not given, input is not given as the graph.
No, input is given as objects. The intersection, I guess, I mean, that's the whole catch in matching and so on, right? You don't want to define the graph. Yeah, I mean, we had like several results using simple and general approaches. The one question, if I have to pick from here, which I find surprising that it is still open. If you have axis aligned line segments in the plane, the best approximation we know for independent set is 2 approximation. And this is basically ignore one axis. Take the projection on x-axis, take the projection on y-axis, solve the interval problem, take the best. This is going to give 2 approximation. We don't know how to beat this. And this is a special case of the rectangle problem. And I think this is where the bottleneck is, that can we get a Peters, can we not get a Peters? But there are also other questions like,
So is the stabbing or is the piercing problem easier in this setting? I mean, like,
no, we don't know constant factor approximation. We only know log of. Piercing is easy if you are fat objects, not for thin objects.
No, but piercing with line segments look like you can't do much, right? I mean, like
yeah, I thought like basically
They
you are
were
stuck. I thought. I mean,
like the best thing has to be very special. Like
So
you get all the intersection points, I guess. And
yes, but you still have to choose a subset of them, right? Imagine that you have a grid, like a complete grid. So I mean, complete grid is easy to just take the diagonal,
Yeah.
but I mean, it's a mix of the grid then.
oh, because you also want to do it in near linear time.
Right.
Always. So there is, yeah, so anything like
sorry, so then I didn't understand the question. So is the question?
No, the two approximation question is without the near linear
Oh, okay.
polynomial, like the
No,
independent
let's say
set question.
I'm willing to tolerate.
Yeah, so for piercing in the low dimensions,
Let's say same thing, 2 dimensions, you have axis parallel line
Right.
segments.
yeah, that is doable
Okay,
for piercing, but no for independent set.
wait, for doable in the sense that you can get the right answer.
Right, right.
Okay.
Constant factor. Yes.
No, constant factor 2 is also constant, right? I mean,
Because that seems like we should just do it.
So even it is known that if you have fat objects, you can get 1 plus epsilon approximation for piercing.
okay.
Yeah. So piercing is much.
So I don't understand your use of the word even for fat objects. So in the sense that
So
isn't the harder situation, is the harder situation thin objects or what?
I mean, it's not
general thin is
always.
harder,
Yeah,
but
generally
but
thin is
if you're getting
harder
too thin, it might be
Yeah.
easier because the biggest.
because then it becomes the line
optimal
segment.
solution itself might not be very.
That is what to hear. So for line segments, axis parallel line segments in a
Yeah.
plane,
Right.
the piercing problem.
I think it
there
is
a-
solved.
There is a 1 plus epsilon approximation.
Probably
polynomial.
exact. No? Or probably-
Exact, I don't know. I don't remember the exact status, but as far as I remember, this is resolved. But independent set is not.
Yeah, okay.
And the independent set, the point is like, I mean, so there is a Q pitas, so there should be a pitas, right? I mean, for all, yeah, but we don't know. And also for the weighted case, is there a constant
No, you
factor?
can just compute all the intersection points, right? So anything that is not an intersection point can only clear one of it.
Yes,
And then all the intersection points, you know exact. Also, is it like a big, like a packing type thing? But
Yes.
it should be something. You have to choose some set of.
yeah. So I think like 15 minutes, I want to speak about packing. So packing setup is following largely. So you have a hypercube. Here I basically have a rectangle, which is a container, and you have a set of objects of particular interest. I'm going to focus on spheres or balls. And I would like to pack circles or like balls inside this container. I mean, you can give like one kind of packing, but the question is that is it the best packing, or can we do like much better than this? So the reason that I liked the ball packing problem, because I'm not from actually packing literature, but the reason I started working on this because it exhibits a very interesting phenomenon. So typically, like a thumb rule for packing literature is this method that Nova Alone and others had, this next best fit mechanism, which is kind of a greedy analog. And this works for all kinds of orthogonal shapes like squares, rectangles, and so on. But if you think of pentagons, for example, this doesn't have a stacking phenomenon. So you can't really like stack things on top of each other. For example, something like this. Now you want to think of circles or balls, and they are like much nicer objects. And but they exhibit somewhat similar phenomena like the pentagons. Because if you pack, let's say, a large ball, then it wastes a lot of space in the corner, and this space cannot be used for packing other balls, for instance. So
What's the problem on packing? So you're given a
we have a container and we have a set of
collection of objects.
right,
and you want to pack
largest sub collection.
largest sub collection, or you want to minimize the space unused? You want to put the largest
Largest sub collection.
largest
Yeah.
sub collection.
So later on, we'll see that we'll actually consider a bit more general, like the profit version. So there is also like profit associated with it, but yeah, I mean, largely that. So like in math, people have been studying packing like for ages, like circle packing, I think started with Kepler. So this Kepler's famous conjecture, or this six-cornered snowflake conjecture, that no arrangement of equally sized spheres filling space has a greater average density than that of the cubic closed packing or face-centered cubic and hexagonal closed packing arrangements. So Lagrange solved this in 2 dimensions, and the 3-dimension proof came in Discrete and Computational Geometry 2006 by Hales and Ferguson. And this famous result by Vyazovska for dimension 8 and 24, it's a seminal work, and for which she won the Fields Medal. We are interested in little simpler things. getting approximation here. So we have it's a geometric interpretation of the knapsack problem. We have a set of d-dimensional objects for some constant d. For example, circles, hyperspheres, balls, but also possibly like other shapes like hexagons, pentagons, and so on. And there is some profit associated with each of these objects. And we would like to choose a subset that is going to give the maximum total profit, which can be packed non-overlappingly inside this container. By the way, like packing objects, this has like many different variations. In like here, translation is allowed, but we are not allowing rotations. Of course, it doesn't make sense for balls, but like for other objects like pentagons and hexagons, that makes sense. I mean, this is a problem that is used in many different industry, like this tree plantation industry, cutting industry, and so on. I'm not going to go in to this. Okay, so let's see that what is known computationally. So Eric Timan and others showed that already in 2 dimension, if we are dealing with unit disks, this problem is NP hard. And for hypercubes in constant dimension t, there is a 1 plus epsilon approximation for this. For other classes of fat objects, now in packing literature, there is a notion called resource augmentation, and that makes like packing problems much simpler. I mean, different. So resource augmentation essentially is that you are allowed to enlarge the container, let's say a little bit, like by 1 plus epsilon. So for circles in the plane, the best known approximation was by Miyazawa and Wakabashi. It was 3 plus epsilon. Now, the first interesting.
In all of these, the container is always a box, or container is also changing in.
Box, yeah.
Container is
Right, yeah.
That's not.
In this work, we are. But people study like container also different than. So we don't know the membership of this problem. We know that this is NP hard, but we don't know if it is in NP. And the reason is because we have to deal with sum of square roots, right? So even given a set of n circles with constant number of different sizes, decide that whether they can be packed inside unit squares, we don't know. So there is a PTAS under resource augmentation. I mean, there are also other works like triangles. There is a constant factor approximation. Geometric knapsack in general do not admit PTAS for 3 dimensions like axis aligned cuboids. There are a lot of work in rectangle squares, hypercubes. I'm not going there. There's different literature. The question that we were interested in is that what are the best approximation ratios that we can get and for what kinds of input objects, and like for what kind of objects we can actually get a PTAS. So if we are dealing with convex polygons and with at least number of sides to be greater or equal to 5, they can be all of different types, like they can have different angles, different number of edges or orientations, but we can get a polynomial time approximation scheme for them. For balls or spheres, we can get a 1 plus epsilon approximation, but there is also this behavior of the irrational coordinates. So we can actually give the rational coordinates for all but constant many of them. So we don't know. So the problem, like in general, is that can you give the rational coordinates for all and get a PTAS, for example? So Mikkel Abramson, Tillo, Mitso, and others like, so I think in Fox 2020 and then in Stock 21. So they showed various classes of packing problems fall under this class of existential theory of reals complete. And a major open question is what happens to spheres or balls? We don't know. I mean, they asked this, but yeah, it's not resolved. And if we knew that there always exists a 1 plus epsilon approximation only with rational coordinates with polynomial number of bits, then we can also like find this. But given this added information. And also if the input objects are sufficiently small compared to the knapsack, you can get a 1 plus epsilon approximation. But this is not very hard to see because I mean this next best fit algorithm, right? So basically if they are very small in comparison to the knapsack, then you can like think of them as like grains. So you create like blocks of spaces and then sort of pour these grains inside this space. So in that case, the scenario is much nicer. So I have 5 minutes. Yeah. So I think I'm just going to very quickly like speak the initial things and then so somebody asked at the beginning the fat objects definition. Here is a formal definition. So if you take an object, take the largest ball inside and the smallest ball containing this object, this ratio is constant. And so for d-dimensional F-fat convex input objects, we can get a polynomial time algorithm, but under resource augmentation, we are allowed to like enlarge this. But then you might question that, okay, I mean, for resource augmentation, I criticize resource augmentation. Now, why am I using the same? But I'm going to use the resource augmentation to actually not use resource augmentation later. So I'm going to define different classes of objects based on their sizes. Given a particular grid decomposition, I'm going to define large circles or large balls. So everything I'm describing in 2 dimensions, they just generalize. If it contains a cell completely, so then this is a large circle. And then we can partition the grid cells for each input objects and containing inside the partitions like a hierarchical manner. Okay, so there is this separating hyperplane theorem that says that I mean, if you have these 2 convex objects, then you can always find a hyperplane that separates this thing. And now this augmentation, you should see it as some sort of a shrinking. Like it's kind of an opposite thing that I'm asking because it helps us to discretize. Think of it that for some subset of objects, I have solved this problem under resource augmentation. But by doing so, what have I done is that I have created a patch of space around them, which is an augmented space. So I'm going to use the small objects as like grains to pour inside this augmented space. So that is the general ethos of this. And like, I mean, largely it works like this: kick out all the middle level objects because I'm going to keep the large objects, I mean, large objects with large profits, do the resource augmentation, use this extra patch of space to pour the small objects, and that should be comparable. And yeah, so I guess I'm just going to guess this. It has like this 3-phase mechanism: the guessing large circles and placing the small circles, and then structural packing for the small circles. And just because of the size of the large circles, it is not possible to pack too many of them. They are the constant many of them. And these are the ones that we don't know who are these people. So we have to guess who are these people. And so, I mean, this is where basically this irrational behavior kicks in. But other than that, for the small circles, it is possible. So one can define these quadratic inequalities and so on. So I guess I'm just, in the interest of time, skip over these things.
So what is this guessing? Is it a probabilistic mechanism?
Sorry?
Is the guessing a probabilistic mechanism?
No, it's just these inequalities. It's not probabilistic. Yeah. And then actually, the funny part is that I remember that at the beginning of this packing, when I was describing this stacking behavior, I said that for circles, there are this wasted space in the corner, but this is exactly the space that I'm going to use for the small circle packing. Every large circle ensures that around the large circle, there is an amount of space which is being wasted. And this is the space that can be used for structurally pack the small circles. But yeah, so this also works for well-behaved polygons. And why well-behaved polygons? Because see, you need some kind of fatness, like this type of objects, they don't help. It's simply a limitation of our framework, because in our framework, essentially what we are doing is that we are using the space created by large object around it to pour the small objects. And if they are thin, then they don't really create much space around it. So that's the limitations. So yeah, I mean, packing, the main issue is this curse of corners. That's the yeah. So some important questions. This irrational coordinates thing that I have already mentioned, and if this irrational coordinates with polynomial many bits suffices, then it should work. So these people asked that if sphere packing is existential theory of reals complete, one can explore other directions like
But
parameterized
rotations are allowed.
So in spheres, that's
Oh, no, but this is for polygons.
for polygons, of course.
Yeah,
Yeah.
only with rotations.
So they have like but these theorems are also like very interesting with the shapes in the theorems. Like some allow rotation, some don't. So it is all kinds of things you want to pack in all kinds of things. Yeah, I mean, we were more mainly asking the approximation questions, but I guess one can also look into the parameterized complexity or other kinds of algorithmic paradigms. One can ask like, okay, what happens to like more general convex shapes that doesn't have the fatness assumption? Or what about like non-convex shapes? There are somewhat for L shapes and this kind of things, orthogonal shapes.
If rotations are allowed, that's very surprising that it's the existential theory completed, because then you're allowed to have transcendent with people.
Possibly, I have no idea what.
So I thought existential theories you can only define algebraic.
I think they allow rotations, but limited number of rotations, something like this. Yeah, but like sphere is clean question. There is no issue of rotations, only translations. Okay, so I think with this, I'm going to conclude this. This is the picture of observable universe and made of all kinds of shapes. Thank you.
Questions?
Yeah.
So, in the first part, you
Yes.
have considered the axis parallel rectangles.
Boxes, yeah.
Yeah, why that's so?
We don't know how to solve for rotated boxes.
Any algorithm in post polynomial time running time for this?
No, I don't know. Like even the previous algorithm of n to the d by 2, this is only for axis aligned case. Yeah, that's a good question. For example, for boxes in general, like where you don't restrict to axis aligned, does there exist a constant factor approximate? I mean a log opt, not constant factor.
Also, it's like this question will be especially asked if you go two or one floor up to two. Is that, have you considered a hyperbolic geometry set of
Oh.
like there also this kind of like parallel lines box system makes sense, but then you can
Yes.
pack like
Yes.
many of them, like far too many of them.
Yeah, I mean,
many things might just work out and many things might. It's very interesting.
yeah, I think these regimes are like, so very recently, like due to basically one friend, like I started looking at this piercing question for hyperbolic objects, but because like, you know, as you go closer to the boundary, then the size decreases and so on. So things are more funky.
When you define the patterns earlier, you defined it for non-convex objects as well. No?
Yeah.
So can you tell us what the definition for non-convex objects is? Pattern?
I mean, so like for any object, right, you can take the largest ball contained inside the object and the smallest ball containing the object. Their ratio is.
That's all.
That's all.
But because you can have some hair-like things coming out, that doesn't bother you.
That does, but because I also made an assumption of constant description complexity that, yeah, otherwise you can create a ball and spike box kind of like, yeah. So then it will be just a problem of defining this, right? Yeah. Yes, so I think like if you as you go like in very high dimension or you have this kind of scenario without any description complexity, you have to work under query model. There is.
If there are no more questions, then let's thank the speakers. Yeah.